All right, this is Balancing Chemical Equations by Rafi, Joey, and Alexey. Today, we're going to be showing how linear algebra can be used to balance chemical equations by showing some history, examples, some theory, and a couple of things which we found confusing while learning. Next slide. History development. The link between chemistry and linear algebra took off in the 20th century when mathematicians and chemists realized that balancing a chemical equation is basically the same as solving a system of linear equations. So before that, chemists balance equations or balance reactions by inspection, basically guessing numbers until both sides matched. That worked fine for simple reactions, but once you got like dozens of elements, it became really hard to do it by hand. So they started representing the atom counts as variables and writing them in a matrix form. Each row corresponded to an element, and solving the matrix gave the correct coefficients. Over time, this approach became essential in computational chemistry and even AI-based reaction modeling today. Next slide. Past uses. Stoichi Linear algebra has been used in chemistry long before it became common in classrooms. One major use is through something called the stoichiometric matrix, where each row represents an element and each column represents a reaction. Scientists use this to apply conservation laws and analyze steady states in reaction networks. In chemical engineering, matrix methods simplify huge mass and energy balance systems, especially when there are dozens of reactions happening at once. Next slide. How to use how to use linear algebra to balance a chemical equation. Every chemical equation obeys the law of conservation of matter. The number of atoms for each element must be equal on both sides. The numbers we place in front of each compound are the coefficients, and those are the unknowns we're solving for. In linear algebra, we can represent this as a matrix equation. Each row corresponds to an element, and each column to a compound. By setting up equations for the number of atoms, we can use row reduction or null space methods to find the correct coefficients. This turns what used to be trial and error chemistry into just a mathematical process. Hello?
All right, so now we're just going to go through the step-by-step method onto how to actually do the linear algebra algorithm and actually balance a chemical equation using it. So first, what you're going to want to do is figure out how many unique elements you actually have inside of your entire equation. Once you count how many there are, what we're going to do is replace each molecule with a vector, and each entry inside of that vector is going to represent a unique atom. So the space that the vector is going to reside in is going to be the number of unique atoms you have. So if you had just three different types of atoms inside of an equation, your vector would be an R3. Um, so once you figure that out, you're going to replace each molecule with that vector, and you're going to assign each entry in that vector with a type of atom. So let's just say you're making water. All you're going to have is hydrogen and oxygen. You could just let the first entry equal hydrogen and then the second equal water or oxygen, or vice versa. It's up to you. Because remember, you can always swap the rows in a matrix. That's one of the things we learned. Once you figure out which um, entry corresponds to which atom, you are going to replace each molecule with that vector where you've assigned that. And in those entries assigned to those specific atoms, you're going to enter the number of that atom inside the molecule that you replaced. So if you had H2 and you're replacing that with the vector that I just talked about, you would write a 2 at the first entry because you have two H's, and then you'd write a 0 because there's zero oxygens. After that, after you do that for all of the molecules, you're going to want to set the entire equation equal to the zero vector, basically. So in order to do that and move the products onto the left side, you are going to just flip the signs of all of the entries inside of the product vectors, and then you can just bring them over to the left side. Once you do that, you can combine those vectors that you've gotten into a matrix with the weights x1, x2, x3 on the outside. And then once you have the matrix, you can just set it equal to the zero vector as your augmented column and row reduce. And it's really simple after that. Then once you've gotten the row reduce matrix, those are basically your values that you're going to have in general, but you need to make sure that you need to make sure that they're whole numbers because in chemistry you can't have a part of an atom. You can only have whole atoms. So you need to make sure each of your coefficients are whole numbers. So you need to scale all of your answers that you got from row reducing the matrix until they are all whole numbers. And once you do that, you have the lowest possible whole number combination of coefficients, and that's going to be your answer to the balanced equation.
Okay, so now I'm going to show how we can balance a simple chemical equation or reaction. We'll use this one as the example. So first, we'll set up what we call atom vectors. So for CH4, the vector would be 1, 4, 0. For O2, the vector would be 0, 0, 2. For CO2, it would be -1. And then for H2O, it would be 0, -2, -1. Okay, so now we can take these vectors and put them into a matrix. And then in the end, once we have this matrix, we'll row reduce it. Okay, so we have our matrix, and then the reduced row echelon form of this matrix is 1, 0, -1, 0, 0, 1, -1, -1/2, and then 0, 0, 1, -1/2. So from this matrix, we're able to rearrange it and solve for the variables. And then in the end, once we found every single coefficient, the equation, once balanced, comes out to be 1 times that molecule, then two O2 molecules. Then the other side would be 1 CO2 molecule and 2 H2O molecules. Okay, so now we're going to balance a combustion equation, which has much bigger coefficients compared to other ones. So here we go. This will be the left side, and then once balanced, it'll turn, or not once balanced. Once the reaction happens, we'll have H2O. Okay, so first, set up the atom vectors, like we call them. We'll have C4, C6, H14 is 6, 14, 0. Then we'll have O2 be 0, 0, 2. Then we'll have CO2 be -1, 0, 2. Sorry about the handwriting. It's hard with the mouse. And then we got H2O. Oh my God. H2O would be 0, -2, -1. Okay? So we'll put this in a matrix like we did last time again. Once we're in matrix form, it's now much harder, but if we were doing this by hand, the row reduction would probably take longer than the other one, which is why it'd be a little bit harder. But so that's our matrix. And then once we reduce it into reduced echelon form, the final matrix will be 1, 0, 0, -1/7. Then we got 0, 1, 0, -19/14. And then for the last one, we got 0, 0, 1, -6/7. Excuse me, I had to cough. Okay, so once we have this matrix, we're able to solve for each of the variables values, and then we'll put them back in front of our original vectors or the atoms. And then in the end, we'll have 2 of this atom, which is, or molecule. Sorry, I'm not the chemist here. That's Joey. 19 of this, and then we have 12 CO2, and then 14H2O, like that. So this is our final balance equation using the linear algebra. All right, so now let's look at how linear algebra actually helps balance chemical equations. We can write every chemical equation as a system of equations, which is essentially just AX equals 0. In this case, A is a matrix that shows how many of each element appear in each compound, and is like the set, and X is the set of coefficients we need to find. Solving the system gives us the values of X that make both sides of the reaction have the same number of atoms. And then, well, like this solution comes from something called the null space, which just means all the ways we can balance the equation. Because most reactions have more compounds than unique elements, we're guaranteed to find at least one solution. And then we use tools like row reduction and Gaussian elimination to find these coefficient ratios quickly and accurately. All right, next slide. All right, so while linear algebra works really well for balancing atoms, there's still a couple of limitations to know. So first off, when you're balancing redox reactions, linear algebra doesn't account for electron transfers or oxidation states, which are key in redox chemistry. And then for second, for charge conservation, it only matches atom counts, not total charge. So ionic reactions might still be unbalanced even when the atoms look right. And finally, chemical meaning. Um, Even if the math gives us a balanced equation, it doesn't guarantee that the reaction actually happens or is chemically realistic. So overall, pretty much linear algebra gives us a powerful tool for balancing, but we still need the knowledge of chemistry to make sure it will happen and make sense. It makes sense in the real world.
All right.
All right, next slide. And then this is our works cited, which includes like the textbook and a couple other sources. Thank you.